this computer. Okay, we're good to go. This is the last lecture of the course. I remember Thursday is when I show the best videos that were sent to me, are actually the most entertaining videos, and the best. So today we're going to talk about life. Oops, sorry, I messed up here. Let us go back to there. Even professors make mistakes. It's rare. Okay. Yeah, I think that's my first mistake this semester. Amazing. Okay, share screen. Keynote. There we go. Okay, so this is the last lecture. Thursday is when we show videos. This lecture is on life on the universe. We're going to talk about three topics here. The first is what is life, life on the Earth, and then life in the solar system. We'll talk about life in the cosmos. There's no mistakes, only happy accidents. Yeah, tell that to the Challenger astronauts. We'll talk about how we search for exoplanets. We'll talk about habitable zone. We're going to go into the detail about something called a TRAPPIST-1 exoplanet system, which is interesting in its own right. And then we'll talk about extraterrestrial intelligence and the search for extraterrestrial intelligence. I've got a lot of slides. We're probably not going to be able to go through all of it. I'll probably eat into the QA session a little bit. So what is life? If we're going to be looking for life in the universe, we got to know what we mean by life. And that turns out to be an almost impossible task. It's kind of like, well, you know, it's life when you see it, but defining it is really tricky. There is no uniformly agreed on definition of life, none. There are some things that are common in definitions. I'm going to list you 6 things. You are not responsible for them. These are just things that show up in most lists, not all of them. Homeostasis, you regulate your internal environment, meaning inside the body of the object or the plant, to maintain a constant state. You're highly organized. You metabolize. In other words, you take stuff in, you do something to it to make it better for you, and then you send stuff out. You eat, you metabolize to turn that into energy and turn it into me speaking, and then you get rid of the stuff. You grow. Which is, these are a little funny because, you know, I don't grow, or I shouldn't. You adapt over time. Does an individual entity adapt over time? I think they're talking about species versus individuals here. Response to stimuli, that you respond to the outside environment and you reproduce, which is kind of weird because an animal that can't reproduce, you would certainly consider it alive, like a donkey or, you know, me. So what is life? Here are these attributes that most people agree on, and it's very confusing, but we can simplify things. The way we're going to simplify things is, what do we need to meet these attributes? What kind of environment do we need? And the first thing that we must have is very complex chemicals. In other words, we must have complexity in the chemical reactions, because we're talking about life that deals with chemicals, not life that deals with nuclear power or weird stuff like that. So we need very complex chemicals. We need some way for those chemicals to interact. And if those chemicals are complex, but they can't interact with each other, then you're nowhere. And of course, you need an energy source. So complex chemicals, a liquid, some way to mix those chemicals, and an energy source. So in terms of complex chemicals, the only element that generates incredibly complex chemicals is carbon, which is why everybody talks about carbon-based life. And the reason why is there's an infinite amount of carbon compounds, carbon molecules. In fact, there's a whole branch of chemistry called organic chemistry. Organic means carbon, doesn't mean alive. And so this is why we are 99.99% positive that if we find advanced life out there, it's going to be carbon-based, because you can't make, there's no other chemical, there's no other element that you can make as complex chemical reactions. Proud to be a carbon-based life form. The liquid to mix all those, that liquid, we really need that. We need it for what we call encapsulation. So you can have, there's you and then there's other. If you don't have any way to encapsulate, then you don't really have an other. Reactions occur faster in liquids. And what is the best liquid in the universe? Water. Okay, water is stable at a wide range of pressures and temperatures that are available. There's a lot of water out there in the universe. It's ubiquitous. It's strong hydrophobic effect. What that means is that oil and water don't mix. And so if you have something that's oil-based, it creates this membrane. And in fact, let's get rid of that annotation. Okay. In fact, I forget where I was. Boy, that's the second mistake I've made today. Water is ideal for carbon chemistry. Carbon molecules love to be mixed up in carbon in water. Strong hydrophobic effect. Oil and water don't mix, and so if you have a membrane made of oil molecules, then you can encapsulate things. And in fact, that's exactly the way cell membranes are made. They have the outside attracts water, the inside repels water. It expands when it freezes, which is interesting because if it didn't expand when it freezes, what would happen is if you're on a planet that has a melt freeze cycle, then the lakes or the bodies of water would freeze at the bottom and eventually the thing would freeze over. The fact that we freeze at the top where it's most exposed to warming environment really makes water unique among all the liquids that are available in the universe. So again, we believe that we need a reasonable temperature, a temperature approximately like what we have on the Earth. We need water and we need carbon. So people say, well, you're really kind of carbon centric here. Yeah, we're carbon centric for a reason. And the reason has to do with the complexity and the ability to mix in water. Here's a nice video. It's a little long, but I think it's worth it. Okay, so as we mentioned in the video, the virus kind of blurs the difference between living and dead. And so again, it's very difficult to come up with a definition of life. We're not going to try and do that in this course. So what we'll talk about is those three things: carbon, liquid, water, energy. And we have one example of life in the universe, and that is life on Earth. And believe it or not, it does have some information about the possibilities of life in the rest of the universe. So we believe that initially we had an atmosphere of hydrogen, nitrogen, oxygen, and then later as the atmosphere cooled, we had methane, ammonia, carbon dioxide, and water. And we think that at this point, when the Earth cooled, that's when life could develop. And so here we had the chemicals, the hydrocarbons, we had water, and we had energy in terms of light from the sun. And then we also had, for our life, amino acids and nucleotides. Here is the timeline of the Earth. The Earth was formed 4.5 billion years ago. You see the cursor there. And then it was destroyed 4.52 billion years ago when a planet the size of Mars slammed into it, liquefied the planet, and out of that impact was formed a new Earth and the moon. And it took another 500 million years for the Earth to cool down enough that those complex chemicals could form and we would have liquid water on the surface. And it cooled down to about 4 billion years ago. And in fact, at 4 billion years is when we have the first evidence for life. So we only have a sample size of 1, but it's an interesting sample. That life developed essentially instantaneously with the ability to support hydrocarbon life. That's an interesting data point. So maybe life isn't that rare. Then we had a couple of events where we had more complex life, but really the only time that we started to develop life that you and I would recognize as life, in other words, plants and animals, that have arms and legs and flippers and leaves and those sorts of things. That happened during what we call the Cambrian explosion, which was 541 million years ago. And then from there, life exploded, and then we get us. And so the dinosaurs lived until 65 million years ago, which is a line right there. And then we're the last little sliver. I'm sure you've seen things about, humans as the last sliver forever. But here's the thing that's interesting, you probably hadn't realized, is that life was developed instantaneously, but it took 3.5 billion years to get to the point where interesting life developed, where you had plants and animals. 3.5 billion years. And so again, it's only a sample size of one, but possibly life is easy, complex life like plants and animals is hard. Interesting to think about. So where could we find life in the solar system? Well, everybody's looking for life on Mars, but there's other places that we can look. The moons of Jupiter, we'll talk about that. Europa is really interesting. The moons of Saturn, Titan and Enceladus, are both really interesting places. And these moons of Jupiter and Saturn are so far away that they can't really get their energy source from the sun. So what they do is they get their energy source from tidal heating. In other words, the flexing of these moons as they get a little bit too close to their planet. So Mars, we know that Mars had liquid water on the surface. So in fact, we are looking for it literally today. The Perseverance rover is looking for signs of Mars in an ancient lake bed. Europa is interesting because we know that it has liquid water. In fact, it has more water than the Earth does. It's just that water is underneath the surface. We know that it has water because every once in a while we see geysers of water, and those geysers of water are happening because the interior of that planet is heated up by the tidal flexing as it orbits Jupiter. Titan is the only moon in the solar system that has an atmosphere. The atmosphere is about the same as Earth's. It's about one Earth pressure. Now it happens to be an atmosphere of methane and nitrogen, so you couldn't really breathe it, but it is interesting that it has that. This is a picture from the surface of Titan. Those are solid methane rocks. Okay. They also have oceans there. Again, oceans made of methane. Enceladus is, yet again, we have the flexing, the tidal flexing. So we know that Enceladus is mostly water. There's lots of water out there. If we're looking for water, the universe is, the solar system is just lousy with water, as is the universe. Okay, so that's what is life. That's life on the Earth, and then life in the solar system. Now let's talk about the search for life in the cosmos, which has been heated up explosively in the last 20 years. Before 20 years ago, we didn't know that there were any planets. Now we know that there's several thousand. So planets orbiting other stars are known as extrasolar planets or exoplanets. So when you hear someone say exoplanets, they're referring to planets that are orbiting other stars. So as of this morning, there's 4,375 confirmed exoplanets. And there's just about that same number of observations that we believe are exoplanets, but they have not yet been confirmed. So there's a whole boatload of those. And if we look at the statistics of the exoplanets we discovered and look at selections effect, we'll talk about that in a second. We believe that every star has at least one planet, every star. So that means that every star out there in our solar system, in the galaxy and in the universe, has at least one planet, and almost always multiple planets. And so there's just a whole boatload of planets out there. And this is new information. 20 years ago, we did not know this. So here's a chart of the discoveries of exoplanets. And it's interesting for a couple of reasons. So we got these red dots, and we have these blue dots. Is it how we investigated that water? Is it possible to drink? So Andrew, the water in Enceladus and in Europa, it's spiked with all sorts of weird salts. We actually obviously don't have a sample of that water, but we just have spectral analysis. And the problem with spectral analysis is that some things will give you nice spectral lines you can observe in visible specters, others don't. And so you don't really know exactly what something is made of until you actually get samples. And that's why we spend a lot in time and money getting physical samples, well, from the moon, but also from asteroids recently. We just did that a few months ago, and the satellite is on its way back to Earth to deliver those samples. But anyway, going back to this chart, the red are discovered in one way and the blue are discovered the other way. But before we get into that, look at what the axes are. This is the separation between the star and the planet. And these are in astronomical units. So the orbit of the Earth around the sun would be at 1 astronomical unit right there. And notice this is the logarithmic chart. In 1 and 10, so Mars would be about there, Jupiter would be there, Saturn would be about there, and then Neptune, Uranus and Neptune would be over here, okay? So our solar system spans like this region here. So 1 astronomical unit, that is the Earth. Here is the planet mass in terms of Jupiter masses. So the Earth would be like right down here, okay? But notice that we're looking at planets that are extremely massive and very, very close to the star. And the reason why is what's called a selection effect. It's very easy to observe big planets close to their star. It's very difficult to find small planets that are far away from the star. And you can see that there's virtually no planets out here in the region where the Earth would be. And so the red ones are done what's called transit detection. In other words, if the exosolar system is edge on to the Milky Way, to our observation, then we will see the planet going in front of the sun. But that planet has to be reasonably big, because if it's a small planet, then the sun is not going to dim very much and we won't be able to observe it. So that's the way most of these are being observed. The blue ones are observed by the spectral lines moving because the planet is orbiting around it. And these spectral line, and as the planet orbits around the sun will change its velocity, change whether it's moving towards us or away from us. The problem is that the amount that the sun moves towards or away from us depends critically on how big this planet is and how close it is. So if it's big and close, these lines will shift a lot. If it's far and small, these lines will shift so little, we won't be able to observe it. And so that's why we have a selection effect. But this is why, if you take the selection effect into account, you realize that essentially all stars must have planetary systems, just based on the statistics. So what's interesting is what we call the habitable zone. If we're looking for life, how many of these planets could be like Earth? The habitable zone is defined as the distance from a star where liquid water can exist on that planet's surface. And remember, we view that liquid water is absolutely critical for life, because it's really the only practical medium to mix complex chemicals such as hydrocarbons. So around any sun, there's going to be 3 regions. There's going to be regions that are too close to that star, that are too hot. There's going to be regions that are too far from the star, which are too cold. And then you got the green region, which we call the Goldilocks region, which is just right, okay? The size of these regions depends on the star. If you have a small dim star, these regions are going to be very close. If you have a big bright star, these regions are going to be pretty far away. And so here is a map of some of the stars we've looked at, some of the planets that we found. Most of them are going to be outside the habitable zone, but a few of them are inside this habitable zone where the temperature is just right, okay? And we'll talk about how we calculate the habitable zone in just a couple of minutes. Here's another cute video.
How does one discover life on other planets? Well, the first thing you need are other planets. Going around our sun are 8 planets, plus Pluto and a bunch of moons and lots of other stuff. But it's a small selection. So your best bet is to look for planets going around any and all stars. Our galaxy alone has 100 billion stars in it, and so there is a lot of hope of seeing an enormous amount of planets as long as we have a way of seeing them. Here are some ways you can see planets going around other stars. The first is the transit method. The transit method is a method of seeing a planet by watching for it block the light of the star. In other words, if the planet is reasonably big compared to the star, when it orbits the star, it could get in our way, and we would see that the light from the star dims and then brightens again, with this very specific pattern which would be caused by a planet transiting in front of it. And in fact, at this point, thousands of planets going around other stars have been seen using the transit method. A second method that people use is a method basically looking for the wobble of a star. A planet like Jupiter can be quite heavy, even compared to the star, such that when it goes around the star wobbles. And when it wobbles towards and away from us, it shifts the frequency of light that's coming towards us. It's called a Doppler shift. And that Doppler shift, happening at a very regular pattern, period, tells us that there's something heavy going around it. A third way is if stars and planets pass in between us and more distant bright stars. That passing can cause the light to be warped a little bit. It's called gravitational lensing, predicted by Einstein. All these methods and more are hopes for seeing thousands, tens of thousands, even hundreds of thousands of planets in the near and immediate future. But then you want to figure out if there's life on any of those planets. How are we going to do that? Well, the best bet is to look at the atmosphere. The atmosphere will contain all kinds of chemicals, and those chemicals could have been naturally there due to the formation of the planet in the first place, or they could be there because something interesting is happening on the surface of the planet. Giant planets like Jupiter and bigger naturally have water in their atmospheres, but tiny rocky planets shouldn't. And they shouldn't because sunlight breaks apart water, and hydrogen is so light it wants to escape light planets. So look for small rocky planets that have lots of water in their atmosphere. Already that will suggest that there is water on the surface of the rocky planet, like oceans. It doesn't prove there's life on the planet, but at least now we're getting more evidence, and we're seeing ways of seeing planets that look more and more like the Earth. A final stage would be to look at that atmosphere and find other things in the atmosphere with abundances, amounts that are unexpected to occur simply naturally. One of those is, for example, oxygen. Oxygen can be something which is produced by living organisms. So if you look at a planet and in its atmosphere there's water and there's large levels of oxygen and perhaps other chemicals that we might expect to be produced by the processes of life, then we start to have strong evidence for the existence of life. To really go the final step, you need really provable theoretical models of what life can and cannot do and what non-life processes can do, and put chemicals into the atmospheres too. How are we going to be sure? We don't know, other than, let's say, direct communication with the intelligent beings out there. However, we do see a path to get closer and closer to eventually answering that question. Are we alone?
Okay, to answer Thomas's question, for the transit method, wouldn't it be possible for some planets to orbit on a planet that wouldn't obscure the star? Yeah, in fact, 99% of planetary systems we cannot observe with the transit method because their solar system isn't edge on. And we know that, and we knew that going in when we put up Kepler and TESS, the two satellites that are looking for exoplanets with the transit method. And so, we would detect X thousand planets. We know that there's 99 times more than what we detect, just based on those statistics. And also the transit method, big and close means that the angle can be a little bit off because the planet could be so big and close. Small and far planets from the star means that the solar system has to be exactly edge on, and that affects the statistics too, but they correct for that. So let's talk about TRAPPIST-1. The thing I find about TRAPPIST-1 is it's a It's a system where we have multiple planets in the habitable zone. And we can do a lot of calculations with equations that you guys all know, that you have learned in this course. And I know you've been complaining that we haven't had many equations recently, so I thought I'd address that with this little section here. So I want to show you TRAPPIST-1. Here's the sun, and here is TRAPPIST-1, the sun, the star TRAPPIST-1 to scale. And notice it's just a little bit bigger than Jupiter. So this is a red dwarf. And here are the planets around TRAPPIST-1. And they're very, very close to the sun, to their star, okay? Much closer than our planets, and that's because, anyway, you'll see as we go forward, okay? Planet hop TRAPPIST-1. And so here are the 7 planets that they've detected around TRAPPIST-1, and this is the Earth to scale. And notice they're all about the same or maybe a little bit bigger than the Earth, okay? Here are some equations. We're going to use the following equations in this. We're going to use the force of gravity equals G(m)(m) over r squared. We're going to use the luminosity of an object is proportional to the radius squared times temperature to the 4th. And we're going to use the fact that the brightness of an object equals its absolute luminosity over the distance squared. These 3 equations. And with these 3 equations, we're going to be able to do a lot of stuff. So first of all, what is the luminosity of TRAPPIST-1? Well, we know its radius, we know its temperature, and we know that the luminosity equals r squared t to the 4th. And here's the sun to scale, 1 and 5700 K. And so just using this equation and using what we know about the sun, we can calculate the absolute luminosity of TRAPPIST-1, which is 0.00052. So it's very dim compared to the sun, but we can calculate this exactly because we know its radius, we know its temperature. Next is, what is the force of gravity on the surface of the 7 planets we've discovered? And the 7 planets are called, well, actually, I'm going to ignore A because A is too close. So the planets we're going to look at is B, C, D, E, F, and G. So TRAPPIST-1b, TRAPPIST-1c, TRAPPIST-1d. And so here the radius of the various planets is given here. The mass of the various planets is given here, okay? And these are all in terms of Earth. So what is the force of gravity on the surface of these planets using F equals G(m)(m) over r squared, okay? And so here the m will vary for each planet. The r, which is the distance from the center of the planet to the surface, will vary. And this will give us the force of gravity on the surface of planets. And notice that they're not that different from the Earth. This is, you'd feel a little bit heavier on C, you'd feel a little bit lighter on B, D, E, and F, and you'd feel exactly the same on G, okay? So we find this very interesting. Next is, how bright is the sun at the location of the orbits of these planets? Here is the distance of the planets from TRAPPIST-1, the star. And notice these distances, they're really close, like 0.01%. Okay, so 1% the distance of the Earth to the sun. Okay, so these are very, very close in. And we're going to use brightness equals luminosity over the distance squared. And here is how bright the star is relative to how bright our sun is for us. And notice B and C are pretty bright. D is about as bright as ours. E is dim. F is about as bright as the sun is on the surface of Mars. So these numbers are interesting. The last one, using an equation that you guys don't have in this textbook, but it's a relatively simple equation, is what is the surface temperature? Okay, it's a very simple calculation, as you can see. It deals with the brightness on the surface. The only unknown is what's known as the albedo. How much of the light does the surface of the planet shine back? Okay. And using this simple equation and using what we know about the albedos of these particular planets, we come up with what the surface temperature is. And look at this. So D and E, the surface temperature here is, 20, 30 degrees hotter than the moon. TRAPPIST-1e is almost exactly the same temperature of as the Earth is. So TRAPPIST-1e has a force of gravity about 75% of Earth's, and it's got a relative surface temperature that's almost exactly what Earth's is. So just using simple equations, we can say 2 or 3 of these planets are definitely habitable. In other words, liquid water could exist on their surface. Now, there are some problems. First of all, these planets are all tidally locked because they're so close to their sun. So one side is cold, one side is hot, so there'll be massive storms. We haven't even talked about radiation. The radiation dosage for these planets would be extreme unless they had very strong magnetic fields. And they have a very high ultraviolet flux. We know that for a fact. And magnetic fields can't shield ultraviolet. Also, small red dwarfs, even though they last for trillions of years, are extremely variable. And we don't think that's conducive for life. Our star is unusual in that it's been essentially constant for 4 billion years over the time that life has developed. And, the Earth's climate has done some pretty wild swings, but, if the sun's output varied by a factor of 3, I think that would have a dramatic effect on the ability to contain life on this planet. And a vision would be very different because most of the light from the sun come out in infrared, not in visible light. However, there's lots of weird stuff on the Earth. So life develops in hot pools, in the deep underground, and mid-ocean ridges, and Antarctic glaciers. So who's to say? Anyway, it's an interesting thing. So now let's talk about not just life in the universe, but intelligent life in the universe. And this is often talked about as the search for extraterrestrial intelligence, or people will say SETI, S-E-T-I. Search for extraterrestrial ETI, intelligence. What can we look for? Well, we usually think of looking for high-powered TV and radio signals, which we've been broadcasting for about 100 years. We can look for radar systems where the intelligence is sending out very strong radio beams, trying to see them bounce off of things out in their solar system or around their planet. And more recently, we've been making expensive use of very high-powered lasers. So most SETI is looking for extraterrestrial signs using radio waves. We've just begun looking for signs of extraterrestrial intelligence using looking for high-powered lasers. So again, mostly we're doing electromagnetic radiation. There's no legitimate scientists looking for artifacts, so I just put that there. So what we're doing is we're using electromagnetic radiation, and not just any place. We're using electromagnetic radiation in the radio band, and specifically right here. And the reason why is the noise that is from the galaxy is at a minimum right in this area. And we have specific radio lines from hydrogen and OH right here, and we call this the watering hole. And the reason why is these are very prominent spectral lines. This is a very prominent area, and so we believe that anybody that's intelligent would say, we can broadcast high-powered radio signals in this region, and it's not going to be wiped out by noise from the galaxy. So this is why most searches for extraterrestrial intelligence using radio telescopes happen in this region here. Okay. This is a radio telescope built in China. I'm sorry, I don't know the name of it. It is by far the largest radio telescope in the world. It even before Arecibo, collapsed, it was quite a bit larger than Arecibo. One of the goals of this radio telescope is to search for extraterrestrial intelligence. Now, obviously, no extraterrestrial intelligence signal has been found yet. If it had been found, we'd all know it. What exactly should we look for if we're looking for extraterrestrial intelligence? Well, again, we're pretty much going to bet that it'll be coming from planets that are in their relative habitable zone. And we know for a certainty that any advanced intelligence would have the same mathematics as we do. We believe that mathematics is part of the universe, not part of your culture. So along those lines, we have sent signals out. This is the very first signal that we sent out in an explicit attempt to attract attention from extraterrestrial civilizations. It shows the DNA, it shows a picture of us, it shows a picture of the radio telescope, and then information about the sugars and bases and nucleotides. Recently, a study came out where someone who didn't know about this tried to decode it, and they felt that without background information, this would be essentially impossible to decode. So, and I would agree with them. This was a nice attempt, but I think it was just a nice attempt. A more modern attempt, well, modern in terms of 1979, was a physical plaque on Pioneer, because Pioneer 10 and 11 were the first man-made objects to leave our solar system. And so they included a plaque that included pictures of humans. And this is a schematic of the spaceship itself, which the aliens would have possession of. And so they can see that humans are about the size of the spaceship. Then they have pictures of the various planets in our solar system, which includes Pluto, which I think they would find confusing. It includes a map of the directions to various radio pulsars. This also is confusing because this no longer maps up with reality. And so I think this would be the most interesting part for aliens of that plaque. Then we talk about Voyager, which happened in the early 80s, which again left our solar system. They're actually still operational. We are still communicating with the Voyagers, almost 50 years later. And they went one step farther. They included not just a single plaque, but what they call a golden record. I got a picture behind me someplace. Oh, actually, it's in my other office. And what the golden record has various sounds and pictures of Earth. So it's much more extensive than that single plaque. And so you can, there's a great book called The Voyager Record, which includes all those pictures and all the music, includes Johnny B. Good on it, a bunch of Bach and Beethoven, and just random pictures like you would see in National Geographic. So what protocol should we follow if a detection is ever made? Here's a documentary on that. There are so many really howlers in that scene. I mean, first of all, she's yelling the coordinates out to the people who actually control the coordinates. Why? She wouldn't know the coordinates. Secondly, all those dishes are pointed at a source, but as you can see, the dishes are moving. It's just, anyway, it makes a great movie. And really the biggest howler of that movie is what I'm about, I'm sorry. The movie is called Contact. It was, I forget that movie is old. It came out in 1997. It's one of the best science fiction movies ever made, Contact with Jodie Foster. It's a fabulous, fabulous movie. And part of the movie was filmed at Arecibo, which is sad because Arecibo is no more. Anyway, one of the biggest howlers in that movie is what I'm about to show you. And this isn't science fiction. This is real. It's a little loud. Sorry about that. I have no way to change the volume of that. I'll have to work on that. That is a signal from 1979. It's called the WOW signal. And we've been arguing over that signal for 40 years. So it's not like, everybody gets all excited, hey, we finally discovered it. The reason we're arguing about it is obviously that signal sounds purposeful, but that's not good enough because there's thousands and thousands of purposeful signals out there floating not only around the Earth, but in deep space. And the consensus now is that that is a particular satellite that we're just intercepting the signal from. In fact, there were signals that we made a big splash about 15 years ago that turned out to be, the signals happened every time anybody turned on a particular microwave in the employee cafeteria. So that's why nobody gets excited when they see a single signal. It takes years of analysis to figure out if it's interesting. So how do we calculate how many advanced extraterrestrials out there? We do it using something called the Drake equation, which is, I'm really sorry about that. I'll see if I can fix the audio on that for the next term, not for you guys. Given what we know about the odds, how do we know how many alien civilizations out there? We use something called the Drake equation. You've probably heard of the Drake equation. You're probably not quite aware of what exactly it refers to. What it refers to is an estimate of the number of intelligent species there are in our galaxy. It is what's known as a wild A estimate. It is just, there's really no hard science behind it. The Drake equation is really a way of categorizing our ignorance. And let me walk you through that. So let's say how many iPhones on this Zoom are running iOS 14, okay? Well, we could break that down. We could just ask, but let's say instead of 56 people on this particular Zoom call, we have 100 million. So what we would do is the number of humans in the population, let's say the number of humans on the planet, for example, the fraction of the humans on the planet that have telephones, the number of phones they have for each person, the fraction of those phones that are smartphones, and the fraction of those smartphones that are iPhones, and then the fraction of the iPhones that are currently running iOS 14. So what we've done is we've taken an unknown and broken the unknown into a bunch of other unknowns. And you think, what's the point? You had one unknown, now you've got 6 unknowns. The point is that some of these unknowns we know very, very well. And some of these other unknowns we don't know that well at all. And so the Drake equation was useful in that regard because it could isolate the things that we don't know well and put numbers on the things we do know well. And so here's the Drake equation. The number of technological civilizations we talk to in our galaxy. There's the number of stars, the fraction of those stars that have planets, the number of planets per star that are in the habitable zone, the fraction of those habitable zone stars that have planets that have life, the fraction with intelligent life, and the fraction of existence during which intelligent life survives. So if the average intelligent species only survives 100 years, then we get a certain number. If they survive 1,000,000 years, we get a different number. And here's the thing. The number of stars in a typical galaxy, we know absolutely, we know very precisely. We know it's about 400 billion plus or minus a few hundred billion. Fraction of stars with planets. We now know that that's essentially 1, which is different from when this table was made. This table was made just a few years ago. And so this number is actually 1. The number of planets per star that orbit in the habitable zone. We believe also this is about 1. Fraction of habitable zone planets where life begins. So these 3 numbers here, we know with very good precision. Now these 3 numbers, we don't know that well. These are just wild guesses. The fractional habitable zone planets and what life begins. Now, the range goes from 0.01 to 1. The reason why I think this number is closer to 1 than 0.01 is because life developed essentially instantaneously on the planet Earth. Fraction of life where some species evolves to intelligence and the fraction of the species evolves where technological civilization survives. These we have absolutely no knowledge. We have no basis. We can just make numbers up here, okay? So this is the lifetime of the civilization, and this is how many planets with life evolve into technologically sophisticated life. By technologically sophisticated, what the Drake equation means by that phrase is life that can transmit signals over interstellar distances. In other words, we can detect them. And so the estimates of the number of technologically advanced civilizations in our galaxy goes from 1,000th to 100 million. Okay, so that's quite a range. So people say, why is it useful? It's useful because now we can focus on the things we don't know much about. So for example, we've existed as a technological civilization for only 100 years. A technological civilization means a civilization that can transmit information over interstellar distances. And so 100 years ago, we did that with radio. Are we going to be around 100 years from now? Are we going to be around 10,000 years from now? Or are we going to be around 1,000,000 years from now? And those numbers are really interesting and have a direct impact on the number of technological civilizations that we can imagine being in the society. We're going to end today's lecture, and we're going to end the course on a discussion of what's known as the Fermi paradox. It's named after Enrico Fermi, who was having a lunchtime conversation in 1950, where this was the kind of the era of UFOs. You know, people were saying, hey, there's a UFO, there's UFOs in Mexico, aliens are invading. And this was after Roswell. And so people were talking about aliens, and his question was, well, where are they? What he meant by this was very interesting. He said that, you know, our planet has been around for 4 billion years. The Milky Way galaxy has been around for 10 to 12 billion years. There are stars in the Milky Way galaxy that are 12 billion years old, not that much older than the universe itself, which is at 13.8. So if extraterrestrial intelligence was even reasonably common, there should have been billions of civilizations that evolved in those 12 billion years. Billions. Maybe there's only a few today, but over 12 billion years is a really, really, really long time. And the question is, over that time frame, you would imagine that at least one species would have colonized not only their solar system, but would have colonized not only their other stellar systems, but would have eventually colonized the entire galaxy. And in fact, if you look at this, even if you don't assume anything, you know, you don't assume warp drives, you just assume normal ways of transporting information and species, it would only take maybe 10 million years. Here it says 3.5 million years. So let's round it up to 10 million years. So you could colonize the entire galaxy in 10 million years. Now, we, a human species, has only been around for 50,000 years. So that's quite an extrapolation. But if technological civilizations, if only one technological civilization over 12 billion years colonized the Milky Way galaxy, we should know, we should see it. We should see signals flying around the galaxy, and we don't. And so Micah, what I said is warp drives are a science fiction term. We don't believe they exist. I was just saying that you don't need a warp drive to colonize the galaxy. It takes a long time, but 10 million years is a really long time. So his question was, we don't see that. So we don't think that there has been a single advanced technological civilization that colonized other stellar systems over 12 billion years. The implication is there's a problem. So what are the solutions to this paradox? One is we're alone. We are the only advanced intelligence out there in at least our galaxy. Second is interstellar travel is mind-blowingly difficult. We know it's difficult, but it's not impossible. We can't hear them. In other words, we just haven't been looking in the right place. It's a dangerous universe. Nobody likes us. Wait, they are here. And then we'll talk about some weird stuff. So if we're alone, either extraterrestrial life is rare or non-existent, intelligent life is rare or non-existent, or advanced technology intelligent life is rare or non-existent. Okay. And if any of those are true, then we could be it for the universe. Interstellar travel is difficult. Well, perhaps no ET has colonized the galaxy because interstellar travel is just mind-blowingly difficult. For example, Project Breakthrough Starshot, which is a currently Starshot, is a current project to send probes to interstellar space, to Proxima Centauri, Alpha Centauri. These probes are going to be powered by light. So 60 gigawatt lasers, thousands of 60 gigawatt lasers will shine their laser light beam on the probe and accelerate it using light beams to about 20% the speed of light. The probes weigh 1 gram. Okay, 1 gram. So interstellar travel is very, very difficult. Not necessarily impossible. We can't hear them. Maybe nobody's transmitting. We're not looking at the right spatial temporal amplitude wavelength limits. Perhaps they don't use radio waves anymore. Perhaps they only use high-powered lasers. Maybe we're looking in the wrong direction, the wrong time, the wrong wavelength, the wrong amplitude. This is really what the whole SETI uh, um, population talks about. The SETI Institute, this is what they believe is true. They believe they're just not looking hard enough, and if they look hard enough, they'll find it. I should mention that the US government spends not a single penny on SETI searches. All SETI searches in the United States, at least, are funded by private agencies. So Paul Allen, may he rest in peace, is one of the biggest funders of the search. Number 4, it's a dangerous universe. It's the nature of of extraterrestrial intelligence to destroy itself, to destroy others. Perhaps they're destroyed by natural events, or it's too dangerous to communicate. I would refer you to the science fiction book called The Dark Forest, which is the second book in the Three Body Problem trilogy. Highly, highly recommend it. It will blow your mind. Should we avoid aliens?
We have this mental image that a flying saucer will circle the White House lawn, land on the White House lawn, and give us a bounty of all sorts of technological goodies to initiate an age of Aquarius on the planet Earth. Personally, I don't think that's not going to happen. For example, if you're in the forest, do you go out and talk to the squirrels and the deer? Maybe you do for a while, but after a while you get bored because they don't talk back to you, because they have nothing interesting to tell you, because they can't relate to our values and our ideas. If you go down to an anthill, you go down to the ants and say, I bring you trinkets, I bring you beads, take me to your ant queen, I give you nuclear energy. So I think for the most part, the aliens are probably not going to be interested in us because we're so arrogant to believe that we have something to offer them. Realize that they could be thousands, maybe millions of years ahead of us in technology, and they may have, well, no interest in interacting with us in the same way that we don't necessarily want to deal with the squirrels and the deer in the forest. Now, some people say that we should not try to make contact with them because they could be potentially dangerous. For the most part, I think they're going to be peaceful because they'll be thousands of years ahead of us, but we cannot take the chance. So I personally believe that we should not try to advertise our existence to alien life in outer space because of the fact that we don't know their intentions. Then the other question is, what happens if they're evil? Well, I think the question of evil is actually a relative question because the real danger to a deer in the forest is not the hunter with a gigantic rifle. He's not the main danger to a deer in the forest. The main danger to a deer in the forest is the developer, the guy with blueprints, the guy in the three-piece suit, the guy with the slide rule and calculator, the guy that's going to pave the forest and perhaps destroy whole ecosystems. In other words, the aliens don't have to be evil in order to be dangerous to us. They might not care. They just might not care about us and in the process pave us over. In fact, if you read the novel War of the Worlds, the Martians in H.G. Wells' seminal novel were not evil in the sense they wanted to torture us and they wanted to do all sorts of barbaric things to humanity. No, we were just in the way. And so I think that is a potential problem. We could be in the way of a very advanced civilization that simply is not evil, but simply views us as we would view squirrels and deer in the forest. So personally, I think that we should not advertise our existence when we go into outer space. For the most part, however, I do think they are going to be peaceful. They're not going to want to plunder the Earth because there are plenty of planets out there that have nobody on them that they can plunder at will without having to worry about restive natives called humanity. And so I think they're not going to come to visit the Earth to plunder us, to do all sorts of mischief. For the most part, I think they'll just leave us alone.
Camille, it's not that there'd be signals from civilizations from billions of years ago. It's that if any extraterrestrial had colonized the entire galaxy, those civilizations over the billions of stars and planets in the galaxy would still be here today, because even if individual civilizations and individual planets died off, there'd be so many left to continue that. There would be a critical mass of a galactic civilization. So that was number 4. Number 5 is we're under quarantine, that there is a galactic civilization, but nobody's allowed to contact us. Number 6 is they're here, but we don't recognize that. Number 7 is just weird stuff, that they're too alien. These intelligence are just not physical. In other words, they're not beings like us. Or perhaps we don't exist. Perhaps we're in a computer simulation. I think there's been science fiction movies on that plot too. This is all speculation. We don't know. And we're out of time, so I can't show you these really fun videos. So I'll just show you this video to end the course. In the grand scheme of you, I'm nothing more
From
than a
this
possum
distant
screaming at
vantage
you.
point, the Earth might not seem of any particular interest. But for us, it's different. Cherish the pale blue dot, the only home we've ever known.
And that's it for today. That's it for all the lectures. Of course, we have Thursday where we'll be talking, showing other videos. I'll open up for questions. I do have a comment from Micah. Why do astronomers think about the Galactic Federation? I'm not familiar with that. I'd like to hear more. It goes. Go ahead, speak up, please.
Last year, there's like an NBC article about it that talks about how the Israeli former defense chief or whatever confirms the existence of extraterrestrials, in that there's a galactic federation, like a government that just isn't allowing us to access alien technology, blah, blah, blah. It seems so bogus. I just thought it was weird that the story cropped up in a lot of popular big news sites.
Yeah,
there's clearly no evidence.
Yeah, it's weird that these things show up in mainstream article outlets sometimes. I mean, so for example, the former head of the was it the Air Force? Came out recently saying that just wait until the CIA releases these UFO reports. And I looked that guy up, and yeah, he was one of those appointees during the last administration that had absolutely zero background in intelligence or in defense. These things pop up. They never turn out to be anything. That I think you go by the statement that Carl Sagan made, that extraordinary claims require extraordinary evidence. I'll look up Galactic Federation, but I can tell you for an absolute fact, it's poppycock. People don't realize it's real easy to say stuff and get people to report on what you said. It's real hard to actually have facts to back that up. Other questions? What do you think about the Abercrombie Drive? So Jacob, so I actually met Professor Abercrombie, and I cannot pronounce his name for life. Very, very nice guy. His drive is exactly correct in that it follows Einstein's theories perfectly, assuming that you can get yourself a boatload of negative energy. And that's a small problem because we don't think negative energy exists. So it's an interesting exercise in terms of the equations of general relativity. The theory of Abercrombie is that you warp space around you. So in your little bubble, you move slower than the speed of light, but relative to the entire universe, you're moving faster than the speed of light. And Einstein's equations allow that, but if you go outside general relativity, there's no place we know where you can get even one molecule of negative energy. This isn't like antimatter. Antimatter has positive energy. This is like negative energy, something that we don't think could possibly exist. So interesting, but not particularly useful. Other questions? Well, thank you, Thomas. That's very sweet of you. And I'll let you all go, and I'll see you guys on Thursday. Bye-bye.